which are recording, and I have a pleasure to present today talk of Vincent Caudrelier about Yang-Baxter maps, reflection maps related with some soliton interaction. Vincent, please, we can start.
Thank you very much, Dimitri, for the kind invitation. Very pleased to give a talk in this Yaroslav seminar series. So yes, here is the title, and essentially I'm going to try and go through the historical development. So from certain quite old work now, really back 10 years ago, that I did with Cheng Zhang. He was my PhD student at the time, and now he's in Shanghai. And now very, very recent work. So it took 2 years, 10 years, sort of link various topics with Wenxiao Li from Penn State University, which is more about trying to understand how reflection maps, which arose in this paper, what kind of Poisson and symplectic properties they have. So here's the plan. Just a brief review of the set theoretical version of it, which was initially proposed by Drinfeld, and then a brief overview of what the reflection counterpart is. Again, as something that's very well known in the quantum case for quantum reflection equation. And we proposed a set theoretical version with solutions. And this all appeared from a very physically motivated question. We wanted to understand interactions of solitons in a multi-soliton solution in the presence of integrable boundaries in the sense of Sklyanin. And putting various notions together, we were naturally led to solutions, to formulating set theoretical reflection equation and finding some solutions. And then ever since that work, 10 years ago, I was wondering there must be a really nice interplay between these reflection maps and traditional Poisson brackets that you find in integrable systems. So for instance, Lie Poisson brackets or Sklyanin brackets. And this will be explained a bit more in the third part, where we try to understand how these two worlds meet for reflection maps. So, as promised, a brief review of the set theoretical Yang-Baxter equation proposed by Drinfeld. So, by that time in '92, of course, the quantum Yang-Baxter equation was very well known. And Drinfeld in some open problem paper mentioned a generalization to the set theoretical context. So when instead of having a vector space here and a map acting on a tensor product of two vector spaces, you just take Cartesian product of a general set and formulate a corresponding Yang-Baxter equation. So now these indices 1, 2, 1, 3, 2, 3 tell you in which copy of the triple Cartesian product R acts non-trivial, and it acts as the identity map on the factor that is not presented. So here it's the identity in the third copy, for instance. So since this introduction, the set theoretical version, because it is so vast, I mean, you can pretty much put every set you want here with more or less structure. So it has appeared in lots of areas, cellular automaton, geometric crystals, the theory of braces in pure algebra. But for me, the main sources of inspiration, also for the talk today, were initially discrete integrable system, where the set theoretical Yang-Baxter equation appears in relation with consistency around the cube and discrete zero curvature condition, and also soliton interactions for models that have internal degrees of freedom or multi-component soliton PDEs. So in those two contexts, the solutions have become known as Yang-Baxter maps. I think this was a term that was coined by Sasha Veselov originally. And also in those contexts, in discrete integrable systems and soliton interactions, there's usually almost always a parameter version of the set theoretical Yang-Baxter equation that appears. So in fact, in this form, it makes it even closer to the well-known quantum Yang-Baxter equation, where you would have a spectral parameter living on some well, a complex valued Riemann surface, for instance. And you can always see actually the parametric version as a special case of the general version by considering X to be just some other set times a set where the spectral parameter lives. So that's a technical detail. But for me, I would be really interested in the parameter version because for soliton models, these require the status of spectral parameters, and in particular contain the information about the soliton velocity and amplitude, for instance. So the set theoretical reflection equation essentially was proposed so Cheng and myself much later, and by the work that I'm going to review just in a minute. And what we wanted to understand is soliton dynamics and interactions for the vector nonlinear Schrödinger equation. So that's going to be my main example today to illustrate all the ideas in the on the half line in the presence of an integrable boundary in the sense of Sklyanin. So it was natural to introduce and call the resulting equation set theoretical reflection equation because it's really a combination of Greenfeld's proposal combined with the reflection equation proposed by Cherednik and Sklyanin. It has found various applications since this set theoretical reflection equation in discrete integrable systems on quad graphs, for instance, or in relation to the theory of skew braces. I will not talk about that at all today, but it's just as a remark. And what does it look like? Well, again, if you have seen the quantum reflection equation before, it will not come as a surprise. So R here is the Yang-Baxter map that would obey the Yang-Baxter equation and is given. It would, for instance, describe which model you're talking about. And then the problem is to find an additional map, so from the set X to X, which would satisfy this equation. And if you can find such a solution to the set theoretical reflection equation, we will call it a reflection map in general. And as before, you can easily imagine a parametric version, which is also very important for our purposes today, because as I said, these are soliton parameters. But then something non-trivial happens as part of a reflection map, another solution B. You have to also solve or finding B actually requires finding an associated involution which acts on the spectral parameter. So this is in distinction with what happens usually in the case of the Yang-Baxter equation, where essentially when you have a solution parametric Yang-Baxter map, it acts as the identity on the parameter space. Okay, so before moving to the physical origin and what type of problem we were considering that led us to this set theoretical reflection equation, I like to show this this video because it contains the two paradigmatic properties that solitons have. Okay, they are well known, but it's always nice to see it in an actual experiment. So here, it's not the nonlinear Schrödinger equation that is the relevant model. I believe it's KdV, but it doesn't matter. It shows the two type of interesting effects. So the first one, see the soliton perfectly reflected on the boundary. So that's maybe the one that's a bit less known. And then the second effect is elastic cohesion of two solitons, which we're going to see in a minute. So we have the two solitons, they interact and they re-emerge just with a shift, but otherwise unchanged. So in this video, we have the two type of processes that we want to understand more deeply for the case of the vector MLS. So the elastic collisions, that was a problem that was solved a few years ago. And then the new ingredient is to understand the reflection at the boundary. So this is the motivation, if you like. And as I promised, so the model of interest for today is going to be the vector nonlinear Schrödinger equation. Takes exactly the same form as the well-known scalar one. Because I want to talk about solitons, I will consider the focusing regime. But now capital Q is a collection of n scalar complex valued fields. And this is the equation with the cubic interaction. So n equals 2 when you had only 2 degrees of freedom was the original model considered by Manakov as an extension of the famous Zakharov-Shabat work to the case where you take light polarization into account. Both the scalar one, of course, as is well known, but also the vector one are amenable to the inverse scattering method. So there is a corresponding lax pair, which you can use to formulate the direct and inverse problem and construct solutions explicitly. So these are just the formulas giving you the form of the lax pair. A lambda is the spectral parameter, sigma is the generalization to the vector case of the usual Pauli matrix. Sorry, there should be a -1 here. My apologies. It should, because in the case n equals 1, this is just the sigma 3 Pauli matrix. And in W, I put the unknown potential and minus its transpose conjugate. So to tackle the problem of constructing solutions, you can write down in general a solution in implicit form when you have both continuous and discrete spectrum. But there was a very important fundamental discovery by Zakharov and Shabat, which is called the dressing method, which actually tells you how to construct a new solution from an old solution by a process of dressing, which when you specialize it to certain well-chosen dressing factors, essentially amounts to adding solitons one at a time. And in fact, this method has been used and is very well known to build non-trivial pure n-soliton solutions, starting from the trivial 0 solution. So I'm going to focus only on that today because I want to talk only on pure soliton solutions. There will not be more complicated backgrounds or radiation. And sorry, is there a question? Oh, no. To achieve that, essentially, because you start from the trivial solution, there is an associated Riemann-Hilbert problem, which amounts to factorizing the identity matrix. But because you allow yourself to consider a Riemann-Hilbert problem with degeneracies, you actually get non-trivial dressing factors, here G plus G minus, and their properties are completely characterized if you describe their degeneracy space at some finite number of prescribed values of lambda. So these prescribed values of lambda are the parameters that describe amplitude and velocities of your solitons, and the non-trivial content corresponding to phase shifts and position shifts in the scalar case is encoded in G plus G minus in the following manner. So what Zakharov and Shabat have shown is that so G plus, which is enough for our purposes, I'll explain why in a minute because of the symmetry of nonlinear Schrödinger, is completely characterized if I give myself the structure of the space where it is degenerate, so the kernel at lambda j. You can show that in the vector NLS, this kernel has to be one-dimensional, and the beautiful, remarkable result is that the space-time dependence linearizes for these degeneracy spaces. And that's actually what allows you to do a lot of explicit calculations in multi-soliton solutions, which I will come back to later on. And this fixed vector, Vj, is related to, or sometimes called exactly, the norming constant corresponding to that zero. So another beautiful result of Zakharov-Shabat paper is that they show that generically the dressing factor G plus is a product of elementary dressing factors, which are known by all sorts of different names, since some Backlund, Darboux matrices, or matrix Blaschke factor. I will probably usually call them simple elements or elementary dressing factors. And they have a very nice form. So it's the identity matrix and then some non-trivial factor of the spectral parameter. And this object is a projector that contains all the space-time dependence of the solution. And these parameters, fixed parameters, are the zeros of the inverse scattering. So when you specialize this result to vector nonlinear Schrödinger using its special symmetry, so imposing ideas from high-loss reduction, for instance, you can show that the Lax matrix U has this symmetry. Then there is a simplification. So these lambda j plus, lambda j minus are related. So lambda j minus is the complex conjugate of lambda j plus. Lambda j plus lives in the upper half plane. And these projectors are Hermitian because of this symmetry. And also for vector NLS, they are rank 1. We'll see later that much of the story goes beyond rank 1. So once you know these dressing factors, you can reconstruct the solution, the multi-soliton solution, by essentially plugging into the Lax pair formula and doing a large lambda analysis. And you recover that Q, which is inside this matrix W, can be calculated explicitly from the knowledge of these projectors. So if you know the projectors, you know the entire dynamics of the multi-soliton solution. So how do you construct those projectors? Well, before I get to that, sorry, I can not. So to construct the projectors, in principle, you just use, you just use the knowledge of the degeneracy spaces. So you impose that the kernel of G plus is generated by this one-dimensional vector here with this space-time dependence, and that fixes the projectors for you. But now comes a very simple but absolutely crucial observation. Nothing tells me in which order I should impose these various constraints. Or the space. So I could start with the first soliton and the second soliton, etc., etc. But from the point of view of G, I can also start from the third soliton, nth soliton. So here, the order is irrelevant. It just specifies this element uniquely, which means that there's a natural action of the permutation group. And this actually has a very strong consequence, is the origin of the appearance of Yang-Baxter maps in this theory of multi-soliton solutions. So let me illustrate what I mean for the case n equals 2, the simplest non-trivial case. So G is what it is. It's just an element of a certain loop group, which we're going to see a bit later, which has two degeneracies, one at lambda 1, one at lambda 2. And I can decide to first fix the degeneracy at lambda 2 and then the degeneracy at lambda 1, or vice versa. And I will get the same element. So it means that these two expressions for two types of projectors, pi1, pi2, or p2, p1, must be equal. And showing that they are, imposing that they are equal for all lambda, so as rational fractions of lambda, actually is what produces a map between these projectors. And this map turns out to be a Yang-Baxter map. So I've already announced the result, but this is what it is. By this simple observation, you immediately have a Yang-Baxter property encoded, modulo some details that I'm going to explain in a bit. So that's the main observation, really. So of course that generalizes to more solitons. Now, if I have a product of 3, 4, etc., that's where the Yang-Baxter equation comes into play. So if I now forget the physical origin and just reformulate what this is telling me, it means that this can be viewed as a refactorization problem for a certain rational function, matrix-valued rational function. So of course, refactorization problems and their connection with the Yang-Baxter equation is a very well-known topic. And here it's a manifestation in soliton dynamics. So in the special case that we're considering, if I take this dressing factor of this simple element, which has characterized by one parameter, alpha, which is complex but not on the real line. And here P, I'm not saying it, but is a Hermitian matrix motivated by the example we have in mind. If your parameters satisfy this condition, then you can show that the equality of these two expressions for the dressing factor, which amounts to the equality of the products of these two elementary factors, has a unique solution. So you can read it from left to right or right to left. It doesn't matter. But for instance, I can say that the p tildes are uniquely determined from the knowledge of p1, p2, and the lambdas. There is an explicit formula for the images, p1 tilde, p2 tilde, in terms of the all the projectors. So in fact, obtaining this formal formula is not difficult. It's simple algebraic manipulation. What is difficult in general is to show that this map is always invertible, to actually have the formula of p tilde p. But when your projectors are Hermitian and with the conditions on lambda, you can show with some work, it's done by Uhlenbeck and Term, that this is the case. It's always invertible. So as a consequence of the unique refactorization property, you can define a map, which of course I'm going to call R lambda 1, lambda 2, because I'm anticipating that it is a Yang-Baxter map. For future reference, let me define a few sets, which are going to be appearing during all the talk. So because I work with Hermitian projectors, let me denote by HN the set of Hermitian matrices. Pn is the subset of projectors, and Pn with a little index subscript k is all the Hermitian projectors of fixed rank. So far, I've been working with projectors of size n+1 and rank 1. So that's when I specify this general construction to the vector NLS model, because perhaps that's not clear where it's n+1, but it comes from the fact that the lax matrices are of size n+1. So now you can show that this map you've just defined is a solution of the set theoretical parametric Yang-Baxter equation on this set. And the proof, well, I only gave the sketch of the proof, but it's a consequence of the fact that if you have now 3 such simple elements multiplied, and you ask that this product is equal to this product with a priori different projectors, but in the same order, then actually necessarily you find that the p tildes are equal to p's. So using this result of uniqueness, which itself is actually a consequence of Liouville theorem, then you can deduce that the map we defined in the previous slide satisfies this property. So of course, probably some of you are very familiar with all these ideas because they're quite familiar in discrete integrable systems, but this refactorization problem is actually the manifestation of the discrete zero curvature equation, and these G's then would be called Lax, discrete Lax matrix in that context. So here I want to take, however, I want to take an extra step because in all this story, if now you remember that these elementary factors are dressing factors, so they have a space-time dependence, which is, remember, which is specified by the space-time dependence of the degeneracy space. So in all these formulas, there is a space-time dependence of the projectors. And you can use that to your advantage to investigate the long-time asymptotics of the projectors, and then what happens from the point of view of the Yang-Baxter map and the Yang-Baxter equation. So that's how this relates to soliton interactions. Now you want a sort of scattering picture where you have an initial configuration of solitons at time minus infinity, where they are well separated and a superposition of single solitons, and then they merge and, well, live their life, and then they re-emerge at plus infinity as well separated solitons. So of course the question is what happens in the meantime in the presence now of internal degrees of freedom. So let me remind you of a few things before posing this question. So if I go back to the reconstruction formula for the solution, as you said, it depends only on the structure of these projectors, but itself, themselves, the structure of the projectors is determined by the structure of the degeneracy spaces. So you have to do a few calculations, but essentially calculating the asymptotic of your solution is keeping track of exponential decay or exponential growth because of the fact that these factors appear everywhere, and the lambdas, they have either, or the lambda stars, they have either a positive or negative imaginary part. So essentially you deal with exponential decay or exponential growth, and by keeping track of this behavior, you can deduce several results on the asymptotic behavior of first the solution and also on the dressing factors. So let me remind you of, again, something that is quite well known in the general theory of integrable systems. So if I parameterize the parameters lambda j of the solitons in this way, in real part of j, imaginary part vj, so that will give me the amplitude traditionally of the soliton, and that gives me the velocity. So with a lot of generality, I can order the velocities so that there is a scattering process happening. And then you can show that the behavior of the general multi-soliton solution asymptotically is as follows. So if it's a sum of one soliton contributions. So those of you who know NLS, they've seen that many times. So the term here with Vj here, so that's the amplitude, that's the phase of the soliton, and that's the inverse Koch envelope of the solitons. And here she's a traveling wave with velocity minus 2uj with some phase shift, plus terms exponentially small. The novelty of the vector case are these vectors here. So now these p's are n-dimensional column vectors. There's a whole bunch of formulas, so I'm not showing you the formulas because they are important in themselves. It's just they're important for what they mean, the role they mean. So in particular, to understand what these polarizations vector are. So the polarization vectors of the asymptotic solutions are related to these beta j plus and minus, and themselves they are related to the true norming constants. So the beta j here and here are the vectors that completely, oops, here. They are the vectors that completely characterize the degeneracy space. So that's what's fixed to define your solution. This is just a scalar factor. So you have some products of scalar factors, and these d's. So d dagger is the important non-trivial object. So it's essentially what remains of the projector Pj when you perform the asymptotic analysis. And again, because of the dependence, essentially these projectors, they behave as block. They become blocks of n times n and just a scalar block. And this is now a product of such dressing factors of size n times n instead of n plus 1 plus 1, which act on your norming constant to give you the up to normalization, the polarization vectors at minus infinity, and the polarization vectors at plus infinity. So again, if I anticipate, I can already give you the upshot of why I'm showing you all these complicated formulas. Is because if I eliminate beta j, I can immediately relate beta j plus to bj minus, which means up to normalization, I'm relating the polarization at plus infinity and minus infinity. And that's precisely the information that I need to understand the scattering of an n-soliton solution in the presence of internal degrees of freedom. So that's what's just quickly to summarize, to first recall what would happen in the scalar case. So in the scalar case, this is just a number, actually, of normal 1. Because of this normalization, the amplitude is already taken into account. So that actually produces just a phase shift. So you recover the well-known results that in that case, you have a multi-soliton solution, which is a superposition of one-soliton solutions, and the interactions can be understood as a succession of two-soliton collisions, and every time two solitons collide, they exchange a phase and they exchange a position shift, and the total effect of a collision with all the solitons is the sum of all these two-soliton collisions. So now, in the vector case, the polarization vector, they play the role of the phase shifts. So to understand in a similar fashion how you can view an interaction of n solitons within a multi-soliton solution as a succession of two-soliton collisions, you need to investigate the scattering map on these polarizations and see if it can be decomposed consistently into a succession of two-body or two-soliton collisions. And that's where the Yang-Baxter map and the Yang-Baxter equation are going to play a role to make sure that this succession, the way you decompose an n-soliton process into a succession of two-soliton processes, should be consistent. So you need a representation of the braid group, or the rotation group. So this asymptotic analysis and the study of polarization, the study of the solution asymptotically was already done by Manakov in his original paper. But the role of the Yang-Baxter map to understand the processes, the way I explained, was not noticed then. It was revisited much later by Tsuchida and Ablovitz, Plenary, and Chubach, and they did identify the role of the Yang-Baxter map, and they computed it for vector analysis. So as I said, to compute it, all it takes is, well, you take, for instance, two-soliton solution, and then you eliminate the beta j between beta j minus and beta j plus, and you get the formula. So let me show you the formula and the result. So you get a map between incoming polarization to outgoing polarization, which takes this form. So you see that the structure of the dressing factors is quite obvious here, identity plus some scalar depending on the soliton parameters. And here you have an orthogonal projector along P2 minus. That acts on P1 minus. And then here you have the corresponding Hermitian projector, orthogonal projector along P1 that acts on P2. So actually these terms are the ones that really mix the 2 degrees of freedom. You don't need to worry about normalization when you study the map as an abstract map of the set. So this is a case where the set is just this n-minus one-dimensional complex projective plane. So you can show by brute force direct calculation or by the refactorisation properties I mentioned before that this is a Yang-Baxter map. So actually that descends from the properties of the Yang-Baxter map we had at the n+1 dimensional level.
Vincent, I'm sorry.
Yes.
Is there some physical motivation for such a map to be a Yang-Baxter map? So some upper order argument of consistency why this map is a Yang-Baxter map?
So the physical argument is, if you imagine you prepare asymptotically 3 solitons with certain polarizations, you let them interact, and then they will re-emerge. They will re-emerge as 3 solitons with some other polarization. But in the meantime, you view all the possible interactions as a succession of 2-body interactions. And you attach a map to each of these 2-body then for consistency, these 3 particles, it's really the same argument as for the quantum Yang-Baxter. For consistency of the three soliton process, and the fact that you don't know which soliton is going to interact with which soliton first, because it's just an asymptotic statement. So you have to allow for the 2 possibilities. Either soliton 1 is going to interact with soliton 2 and then with soliton 3, etc. Or that, but you don't know, because at any finite time, you know, a multi-soliton solution is just a big mess. You just know that asymptotically in the future, they re-emerge as 3 well-separated solitons. So whatever happens in the meantime, if it factorizes, it must factorize with a map that satisfies the Yang-Baxter equation. Does that answer your question?
Yes. So you said that the process between 3 solitons doesn't depend on the order of pair interaction. But why it is so?
Because it's an integrable model.
Okay, but principally your answer satisfies me perfectly.
No, so sorry. So I know I don't know how much of this argument could be translated in the classical setting, but in the quantum field theory, where you interpret integrability by the presence of higher spin conserved charges, then there is a theorem by Park back from the 80s maybe, which shows that using even only one of these higher charges, you can prove. So yeah, you can prove that in a 3-particle process, using the additional conserved charges, essentially, even it can never be a 3-body process, because you can use the additional charge to shift the space-time point at which the particles interact, and then you always decompose it into a succession of 3 2-particle processes, and then that generalizes to n. So it's the presence of higher conserved charges that, in the quantum case, can be used to prove that this must happen. Perhaps one could also adapt this argument in the classical case. But in any case, it's the integrability that is ultimately the reason for the fact that it is true that this happens.
Yes, thank you. I heard, however, that sometimes it is a tetrahedron equation which interacts, which describes the three soliton processes. So in this case, the consistency condition is the higher order equation. So which parameter, which property of the model is responsible for the order of the n-simplex equation and responsible coherent with this process.
So I think that would be the dimension of the space-time dimension of the model. So for Kp, you would have tetrahedron.
Okay, perfect.
Because it's two, yeah.
Thank you. Excuse me for interrupting.
Sorry, no, it's okay. It's okay. It gave me an opportunity to look at the time, and I think I need to go a bit faster because maybe that's too trivial. Okay, so now I want to move to the problem we looked at originally, which was the same problem, the vector NLS, but with boundary conditions. So Sklyanin introduced some criteria to identify when some boundaries are integrable, but at least in the classical case, it was there's no clear solution method. But Abibulin and then Tarasov-Bigbaev, they came up with a practical solution method. And the idea is to map the problem on the half line to a problem on the full line with twice as many solitons, but with certain Z2 symmetry on the scattering data. And if you choose your symmetry well, then you can use a solution on the full line, restrict it on the half line, and it will give you a solution to the problem with certain boundary conditions. So in particular, we applied these ideas for vector NLS, and we found that there are two nice classes of boundary conditions of the simplest type. Either all the components in QC the same boundary condition called the Robin boundary condition, parameterized by parameter alpha, or depending on the components you look at, sorry, that should be a little Q, some components will see Dirichlet and some will see Neumann. That looks a bit trivial, but if you remember the global UN invariance of vector NLS, then actually you can have a mixture of Neumann and Dirichlet. So we'll see that gives us a nice, interesting class of reflection maps. So what's the philosophy? So I'm not going to give all the details, just really the ideas because it's pretty nice. So the idea is what I was saying. So if you want to construct a solution on the half line with n solitons, let me represent the boundary by this stretch line. What you do is you actually construct a solution on the full line with twice the number of solitons, but they are paired in a non-trivial fashion. So soliton 1 is soliton n+1, soliton 2 n+2, and n is paired with 2n. And the way they are paired is as follows. So the parameter that corresponds to the soliton on the left, j plus n, is minus lambda j star, the parameter of the soliton on the right. And this has a very nice physical interpretation, if you remember real and imaginary part of lambda, because it tells you that the solitons have the same amplitude by looking at the imaginary part, but they have opposite velocity, opposite and equal. So they move towards the boundary with the same velocity. And then you have the more complicated condition. So a condition on a norming constant, which involves, so the norming constant for soliton J, the norming constant for soliton J plus n. It involves a matrix which tells you which boundary conditions you're looking at. So either Robin or mixed, Neumann, Dirichlet. But then it also involves this matrix, which is horrible. It's a residue of a cofactor matrix of the scattering coefficient A, which is a matrix n times a matrix in the vector case, which means that in there you actually have all the norming constants, all the other solitons involved. This is highly nonlinear actually in the betas, this condition. But then Oh, again, that's the idea of the mirror image. So if I want to construct a one-soliton solution with boundary conditions on the half line, actually construct a two-soliton solution on the full line. So the real soliton and its image, and this condition on the norming constant is precisely precisely done in such a way that the correct boundary condition appears at x equals 0. So I was saying these constraints on the scattering data, they look horrible from the point of view of the norming constants, but then there is a miracle that happens. If you translate, so there is it's a hard calculation, but if you translate what it means on the polarization vector, then it's a very nice linear relation. Essentially, the polarization vector of soliton J is related to its mirror polarization vector by a very simple matrix. Again, two types, either for the Dirichlet condition, Robin condition, or the mixture of Neumann and Dirichlet, which is just plus or minus 1 on the diagonal. So that's absolutely miraculous, and that simplifies our life a lot, because now I know how to calculate or how to understand the scattering in the presence of a boundary. So imagine at minus infinity, I have my 2n polarization of the 2n solitons, but really I only care about these ones on the right because they're the polarization of the real solitons on the half line. Then because of this pairing, actually the ones on the left are nothing but the ones on the right with this matrix. And the process I'm interested in is going to be what becomes of these n initial polarizations. So to answer this question, I can look at the case n equals 1 only. So one polarization, but I know how to compute the effect of a polarization before and after interaction when I have a two-body soliton collision. I use the R map. So all I have to do is to fold this R map. So I say that this parameter j plus n is related to lambda j by the Z2 symmetry. And at the same time, I remember that this guy is m times pj minus, and also this guy is m times pj, sorry, the other way around. This guy is m times pj plus. And effectively, I throw out this half, and I have this effective picture that the boundary map, or the reflection map that tells me how a polarization is reflected, is now the result of this folding. So I can calculate everything now and have this map. And even more beautiful is that this folding picture is going to give me a proof, very direct proof, that this is a reflection map by knowing that this satisfies the set theoretical Yang-Baxter equation. So, of course, the fact that it works, this folding, is because I chose integrable boundary conditions. In general, the folding will not necessarily work. I have the, if you like, the mirror image construction has to survive or has to be compatible with R. Otherwise, it wouldn't work. So if you do the calculation for the examples we had, you find an expression for this map from CP1 times this spectral parameter space. And you see the boundary map has a very similar structure to the Yang-Baxter map, unsurprisingly, because it's derived from it, identity plus some orthogonal projector. And here you have the memory of the boundary. So remember, this matrix M is whether you have Robin boundary conditions or Neumann or Dirichlet. And so for Robin boundary conditions, it's a bit of a boring map because when you work with CP1, everything is up to normalization. M in that case is proportional to 1. This orthogonal projector on P just gives you a scalar because it's the projector on P. So up to normalization in CP1, that's just the identity map. But it's still non-trivial information. It tells you that the identity map is always a reflection map. You have more interesting solutions when you look at the mixture of Neumann-Dirichlet boundary conditions and you remember the UN invariance of vector NLS. Then you have this family of maps. B, which I'm going to show in a minute, are reflection maps. Okay, so that's the theorem. It satisfies the theoretical reflection equation, and you can do the calculation, but really there's a beautiful diagrammatic proof. What you do is you use the fact that R satisfies the Yang-Baxter equation, and you apply it for 4 particles, or 4 solitons, paired 2 by 2. So you pair 1 with 3 and 2 with 4. Then you have only 2 possibilities of factorizing 2 by 2. This is equal to this thanks to the Yang-Baxter map. And now you fold. Okay, by the folding construction, this gives me this half of the reflection equation. This gives me this other half of the reflection equation. So they have to be equal. So you can check everything with calculations, but this is really the proof in one picture. And of course, you see the similarity with a non-line representation of the quantum reflection equation. So the polarization scattering map, now the map of interest is, as I was saying, when you're on the half line, you have 2n solitons, but really you're interested into this half and what happens to it eventually at t tends to plus infinity. So we want the map from this initial set of polarization to this final set of polarizations. And just like for the Yang-Baxter case, now when you view the collisions as a succession of 2 soliton collisions and reflection on the boundary, then this map is decomposed into a product of R and B maps. And the fact that it can be decomposed consistently into products without knowing the order is ensured by the Yang-Baxter equation and the reflection equation. So for instance, you have 2 representations when you have 2 polarization of this map. And one way of writing it is like that. The other way is like that. And the fact that it gives you the same final map is precisely the set theoretical reflection equation. So, and I always like to show this picture because you can see the reflection equation actually when you plot 2 soliton solutions. So that's the plot of the 2 soliton solution reflecting on the boundary, and one with slightly shifted parameter. And this is just the reflection equation that we had here. It's very nice to see it on the solutions as well. Okay, so let me see. Right, sorry, I have 5 minutes actually to give you the new results. So in the scalar case, already in the book of Faddeev-Takhtajan, it's very well known that when you interpret the scattering transformation on the soliton parameters, multi-soliton parameters, it's a canonical transformation for a certain Poisson bracket derived from the Sklyanin bracket. So of course, it's very natural to ask the same question for the vector nonlinear Schrödinger equation, first on the full line and then on the half line. So to answer this question, here, these notations, so these are the position shifts, and these are the phase shifts, the phi j plus phi j minus. So in the vector case, the phase shift becomes the polarization. So we need to understand how the polarization scattering map, what Poisson properties it has. The problem is simplified because we said that the scattering map is a product of Yang-Baxter maps in the case on the full line, and it's a product of Yang-Baxter map and B maps in the half line. So really what all you need to do is to understand the Poisson properties of R and B individually, and then you can just take the product Poisson structure. So the first observation, instead of just doing vector NLS, I mean, that was the motivation. The first observation is that actually you can solve the problem for projectors of arbitrary rank, not just one. So now we forget vector NLS and just consider maybe a more general multi-component NLS and work with projectors of arbitrary rank. And the same result holds. You can refactorize. All the formulas are the same. The result is the same. So you obtain also a map now on projectors of arbitrary rank. And the question is, what Poisson bracket should I put on the set of projectors so that this is a Poisson map? That's the first problem. Problem 2, which I'm not going to talk about. It's to lift the problem to a more abstract group level. So that's the question at the projector level, but you can lift at the group level, but I don't have time. Problem 3, same question for the problem on the half line. So now you need to study the reflection map. So that was the content of our more recent paper. So solution to problem 1, how do we know what Poisson structure to put? Actually, in integrable systems, it's very nice because you always have a few usual suspects to work with. Either it's a Lie Poisson bracket on some cohesion orbit, or it's a Sklyanin bracket, essentially, on the corresponding Lie group. So here, if you notice that the set of Poisson, the set of projectors of size n can be foliated with this interpretation that it has can be seen as a coadjoint orbit. So here I say the set of projectors of rank n in the space of size n can be seen as a coadjoint orbit with this identification through a point ek, so identity map of size k and 0 there. So immediately, if you make this observation, you think that the right Poisson structure to use is the Kostan-Kirillov Poisson structure. And indeed, it's the right thing to do for many reasons, which I don't go into detail, but this is one of the reasons. And if you use this Poisson structure, you can establish that this map with this Poisson bracket, so you now consider the product Poisson bracket is a Poisson map. And the easier way to see it is actually to work at the level of the Kostan-Kirillov symplectic form and to look at the reduced map on projectors of rank K and projectors of rank L, because these are the symplectic limits actually of this Lie Poisson bracket. And then you can show by direct calculation. It's a bit long, but it's a direct calculation. There's no abstract fancy argument that this is a symplectic map.
Are you talking about the solution of the Yang-Baxter equation now, or of the reflection
yes.
equation? Okay.
Oh, sorry. So that's as a warm up. So this is a Yang-Baxter map, solution of Yang-Baxter equation.
Okay.
It is a Poisson map for this reason. Now I'm going to tell you very quickly how you can deduce the property for the reflection map. So I skip the group part. Yes, that's still the root part. And I go immediately to problem 3. And here is the strategy. You use the folding, actually, it's very beautiful. So the observation that I made is that you can, the construction of a solution on the full line, you restrict it to the half line, and then you have symmetries on the scattering data. These symmetries on the scattering data, they represent the action of Z2. So there is an involution. Okay. So if you introduce the correct involution more abstractly on projectors, and you show that it's Poisson with respect to an appropriate structure, then you can use the folding to deduce the properties of the reflection map from the properties of R that I've just told you, and the fact that the involution is Poisson. So let me give you the involution you should use. So on the projector of rank K, you simply conjugate it by a unitary matrix, which is related to the matrix M that encodes Neumann and Dirichlet boundary conditions. It is an involution, and if you equip this with the same symplectic form as before, the Kostan-Kirillov symplectic form on this coadjoint orbit, then you can show that sigma is a symplectic map. And now with that, you can, sorry, let me skip that. The trick is as follows. You make the observation that your reflection map can be viewed as a composition of 3 maps which are symplectic. The first one is the involution, which we just say is symplectic, and the identical map, that's symplectic. The second one is a map that is deduced by folding from R, and that's symplectic. Pi is the permutation operator, just so that's symplectic. And then this is an invertible map, which was symplectic, so you take the inverse. So the whole thing is a symplectic map for the Kostank-Kirillov symplectic form that we introduced before. Sorry if I'm going a bit fast, but that's the upshot. And you can also make things a lot more abstract at the group level, loop group level, but I will not tell you more now because I'm running out of time and I want to see if there are questions. Sorry for rushing at the end.
Thank you very much. Vincent, am I right that the reflection map is symplectum, is a Poisson map for the linear bracket? Just for the okay.
Okay. There are two levels that say, so yeah, it is a symplectic map for the linear bracket when you define it on the projectors, which are inside the dressing factors. So let me, sorry, yeah, I knew I was going a bit too fast. So this map here is a map that takes a projector into its image. And this one is symplectic with respect to the linear Poisson bracket. But if you remember, so the part I didn't have time to mention is that, where is it? Yes. You see, the projector is just one element into this elementary factor. So now that lives in the loop group. So you can lift the entire story to a product of such object and have a reflection map that acts on at the level of the loop group. And then it's the quadratic Poisson bracket, the Sklyanin bracket, for which it is symplectic.
Yes.
As you would expect, you go essentially from the linear level to the group level. So you go from a linear Poisson bracket to the Sklyanin, the quadratic bracket. So that's, as I said, that's what you would expect from general philosophy, but to prove it, it takes quite a lot of work. So there are two types of maps that we did in our work, inspired by vector NLS. There's the one just on the projectors, which is the most direct one you see from the physical model. But then once you see that, you can say, oh, maybe I can forget the physical model and then go one level up and work at the level of the Poisson group. And that's what we have done as well. But sorry, I didn't have time to present a bit more.
For me, it's perfect. And I have maybe two principal questions. Are there some steps, generalization or degeneralization? You see, your case is middle quantum, middle classical. You have a map, so which is principally an operator and an object of the quantum world, and you have a Poisson bracket, which is relevant to this map. So the first question is the classical analog of the operator. So you see maybe that it is known the reflection Lie algebras. Lie algebra of the reflection type, which is sort of classical analog of the reflection equation of the quantum. So
do you mean the classical reflection equation that it appeared in Sklyanin's 87 paper?
Yes.
Yes. Okay. So at first, yes, but very long ago, I thought they would be okay. How do I answer the question? Yes.
Vincent, maybe it's a question for long discussion because it's very interesting for me.
Yeah, you see, there are subtleties because, so the thing that is quite amazing is that because even though you look at classical system with classical solution interacting, it's the quantum Yang-Baxter and the quantum reflection equation that appear is the one you see that are quantum. The objects are not the usual endomorphisms or universal matrices that you would do in the quantum world. They're maps on certain sets, but the structure is the same. And that structure is not the structure you get for the classical reflection equation or the classical Yang-Baxter equation.
Yes.
So it's to me, when I remember when I was first studying the interaction, it's amazing because it really shows that solitons are like quantum particles because they interact like quantum particles, but they have, that's as far as it goes. I don't know if I'm answering your question.
But, not completely, but I hope we can discuss later.
Maybe we can discuss more. I think I understand. You want to know where the classical reflection equation is in this story. I know.
But the second question is, where is the quantum analog of the Poisson structure?
Ah. Okay, so like some Yangian or some yeah.
So we could consider, I suppose we could consider non-commutative solitons and consider some structure on their parameters, on their asymptotic parameters.
Oh, I see what you want to do. Some sort of Q-deformed solitons, which maybe would lead to then seeing the quantum structures as opposed to the Poisson-Lie structures.
But
yes.
I hope that from some point of view, it could be more natural to consider both sides of the same nature.
Yes. So the short answer is I have no idea how to do that, but it's a very interesting point. Yes. But
Vincent, thank you very much. Thank you very much. I'd like that we continue this discussion, maybe in private communication, maybe as another talk on at our seminar. So, but for the moment, thank you very much. It was very interesting.
Thank you, Dimitri. Thank you. Bye-bye.
Fine. We stop here. Bye.